So good evening guys. Today's lecture is on torsion in shafts and it would be a quick revision lecture. So let us revise torsion in shafts. So you see torsion or twisting moment or torque are some of the synonyms we use for the torsion. So you see this is a circular shaft or a solid circular shaft which is subjected to a torque, and the torque is always along the longitudinal axis of the body, whereas moments like these in the y plane or like these in the x plane are nothing but bending moments or moments. So the formula of torque is synonymous to the formula we have in the bending moment chapter. That is, in the bending moment chapter, the equation of pure bending is given by sigma by y equals to m by I equals to E by R. Similarly, in the torsion chapter, we have a equation of torsion. This was our equation of bending or bending equation or equation of pure bending. So similarly we have something for the torsion chapter. It is, whereas here we had bending stress, here we have shear stress. Here we had y, which was distance from the top fiber towards the centroid or from centroid towards the top. Here we have radius. Similarly, corresponding to bending moment, we have twisting moment or torque. I'll denote it by TR. In place of the moment of inertia I, we have here the polar moment of inertia. In place of Young's modulus, we have rigidity modulus given by G. And in place of 1 by R, we have L by theta. So this is the first thing. Now let us see some other things in this quick revision. So using this equation, I can write tau in terms of torque and polar moment of inertia, and from here we go here where shear stress due to torsion can be equated as torque over polar moment of inertia denoted by J times R. R is the radius. That is, tau is linearly proportional to R. Hence the graph or shear stress distribution in case of torsion is varying as a linear graph, which is 0 at center and it is maximum at the surface of the solid shaft. So here is the polar moment of inertia. It is calculated as Ixx plus Iyy, and this comes out to be pi d4 by 32. Similarly, we have a comparison of the, you can say, maximum shear stress that in case of the torsion and maximum bending stress in case of the pure bending. In here we have torque by Zp, which is polar section modulus. In here we have bending moment over the section modulus. The polar section modulus is calculated by polar moment of inertia over the maximum radius. The section modulus in case of the pure bending is calculated as moment inertia over the maximum distance from the maximum distance towards to the top fiber or bottom fiber from the center of the cross section. Similarly, we have these equations we just discussed. Then we have shear distribution due to shear force. As you can see, shear distribution due to shear force is quite different from what we have in the shear stress distribution in case of the torsion. You can clearly see here the graph actually varies parabolically, be it for circular section or rectangular section. When shear force is involved, shear stress is maximum at the center and it is minimum at the surface, whereas where torsion is involved, the opposite happens. It is 0 at the center and it is maximum at the surface. Here again, polar section modulus is written as J by R max, and which we can write as pi d cube over 16. Similarly, we have the comparison. So is the comparison between the section modulus of a solid shaft and polar section modulus of a solid shaft. So you see, the section modulus pi by 32 d cube often comes in use in the bending stress chapter, where we have to find out the bending stress m by z, and in that z is taken as pi by 32, whereas the polar section modulus will come handy when we have to find out the shear stress in torsion, which is T by ZP. Here ZP is pi by 16 d cube. Again, we have maximum shear stress, tau max given by T by Zp. For solid shafts, Zp is pi by 16 d cube. Therefore, T max for a solid shaft is 16 T by pi d cube. This formula comes in handy. And for a hollow shaft, we calculate the polar moment of inertia as pi by 32. In the solid, we have pi by 32 d to the power 4. This in here we have pi by 32. D is the outer dia minus small d is the inner dia of a hollow shaft. So we know the factor which is denoted either K or N, which is the ratio of the inner dia to the outer dia of the hollow shaft. This formula can be converted into this form, that is pi by 32 d4. This is the formula of what? Solid shaft also, into 1 minus K4. We have to keep one thing in mind, that the D for a solid shaft is not always equals to the outer dia of the hollow shaft, and when they are not equal, it does makes a difference. And when they are both same, that is the dia of a solid shaft given by delta D and the outer dia of the hollow shaft also D, it makes another case where we have to compare the weights or the torsion carrying capacity. Similarly, we have the polar section modulus for a hollow shaft. Hollow, it is pi by 16 d cube times 1 minus K4. So here I have made a formula flow curve where tau max for a hollow shaft is 16 T by pi d cube over 1 minus K4, and that for the solid is 16 T by pi d cube. This is the stress variation in case of a hollow shaft, where you can see we get a hatched section, and in here we have no material, so nothing comes in here. So we have two things which we can compare side by side. One is the torsional capacity that comes in the torsion chapter, and there is flexural strength that comes in the bending stress chapter. So it is given by tau p times zp, and here it is given sigma p into section modulus. Here we have permissible shear stress times the polar section modulus. Here we have permissible bearing bending stress times the sectional modulus. Another thing we have in this chapter is the angle of twist given by T dot L over G dot J. Often a lot of numericals come using this formula. And then we have power transmitted by the shaft. It is given by T into the theta. Theta is the angle of twist in the shaft, which is further denoted by 2 pi f, where f is the number of rotation per second, which has the units of per second or hertz. You see, not only this formula comes in handy, another formula is often that often comes in handy in different numericals is this one. We have tau by r equals T by j equals g theta by L. So sometimes even this formula can also be used, where I can calculate theta as tau times L over r. This formula also comes handy in certain problems. So you get the gist. You get the gist is that you will have to use the equation of torsion to solve numericals many times. Here's another question quick revision of the power subtopic within the torsion. Power in watts is calculated torque into the theta. Theta is written as 2 pi f, where f is the frequency, where torque has the units of Newton meter per second. Newton meter is also written as joules, so it becomes joule per second or watt. Now RPM, rotation per minute, is represented by n. Therefore the frequency RPS, which is we can see in the formula, this is written as n over 60, because this is revs or revolutions per minute by 60. That will give us the revolution per second. So in the formula of power, we can write 2 pi nt by 60, where it is important to know that n is in revolutions per minute and t is in Newton meter, and this is in watts. Therefore in kilowatts, this is an important formula. Power is taken as 2 pi nt over 60,000. Then we have the torsional stiffness. It is shown by K, which is equals to T by theta, where torsional stiffness is defined as the torque required to produce a unit angle of twist. Similarly, we have torsional flexibility, which is just the inverse of torsional stiffness, which we can write as theta by T. And now we have a question, since the lecture is concept through questions. So here's the question, that it says, if a circular shaft is subjected to a torque T and a bending moment, so it is a case of combined stresses, then the ratio of the maximum shear stress, that is tau max, to the maximum bending stress, that is sigma b max. Now let us see, we have a case of torsion along the longitudinal axis and the moment or bending moment along the lateral axis. Tau max is written as T by ZP, whereas bending moment maximum is written by M by Z, section modulus. Taking out the ratio, we get T by M into Z by ZP. We know Z for section modulus for a solid shaft. We know polar section modulus for a solid shaft. Solving this, we get the ratio of maximum shear stress over the maximum bending stress in case of a combined stress is given by T by 2M. And very often we also get the inverse, that is sigma b max over tau max. That is, I may write it as sigma b max over tau max in combined stresses can also be written as 2m by t. Some numericals can also utilize this relation, or ultimately you can remember one. This is an important result. And then we have these two formulas very usually asked in SSC JE, RRB JE like exam, where we have to find out the equivalent bending moment and the equivalent torsion moment. So we can say then m equivalent is 1 by half bracket m plus root under m square plus t square, and t equivalent is written as root under m square plus t square. This can also be written as 1 by 2 the equivalent bending moment m plus t equivalent. Now let us see, 1 degree is 180 degrees pi radian, therefore 1 degree can be written as pi by 180 radian. Torsional rigidity is given by Gj. Since we have we also had the similar to the torsional rigidity, we had the bending rigidity as EI, we had the axial rigidity as AE. This was the bending rigidity and this was the axial rigidity. Therefore theta is TL by Gj. Gj is the axial rigidity written in terms of TL by theta, that is for unit twist and unit length. This becomes 1 and this becomes 1. The torsional rigidity is equals to the torque provided for unit twist and unit length. So we see it was just relating the torsional rigidity in terms of the unit twist and unit length and the torque. Again, torsional stiffness is the torque required to produce unit angle of the twist. Torsional flexibility is just the opposite of it. Here we have the long shaft of dia D is subjected to the twisting moment T at the ends. Then the maximum normal stress acting on its cross section is equals to. So you see, for a shaft which is supposed to opposite twisting moment T on both ends, it only experiences the shear stress tau. It does not experience a normal stress, which will come only in case of a bending stress. Therefore, since there is no m, it is 0. Here's a summary table. It says for a pure torsion, the maximum shear stress tau max is 16t by pi d cube. It is in the cross section, transverse cross section. That is, you will observe it when you see the cross section. You will see the variation of the shear stress as something like this. Similarly, we have the maximum principal stress as 16t by pi d cube, but the normal stress on the cross section is 0. You see, actually using the Mohr circle, what we get is sigma 1 comma sigma 2 for pure torsion is nothing but tau comma minus 2, which both are, this is shear stress, which for both is 16t by pi d cube comma minus 16t by pi d cube, which represents their opposite nature. Here is another question which asks, the pure torsion of a shaft produces what? Does it produces longitudinal normal stress? Longitudinal? No, it doesn't. Does it produces normal stress? तो produce नहीं करेगा pure torsion anyhow. Only direct shear stress in the transverse section? No. Circumferential on the surface? No. So it is both a longitudinal shear stress and a circumferential shear stress on the surface of the element. जो हमने शुरू में shear stress का variation देखा था, that was basically the circumferential shear stress, where we were checking out the shear stress along the circumference. But what is seen is that through its longitudinal axis also, if we get to have a chunk of this section, we find that there is a variation in the longitudinal length also, that also varies, and that is also a shear stress only. It is not normal stress. I'll show you with the diagram. So we have two types of stresses in the pure torsion. One is the circumferential stress, which is shown in here, which we generally discuss. There is another one which is called as the complementary shear stress in the longitudinal plane. It varies like this. We have to cut the solid shaft, and we see that it varies along the longitudinal planes as a complementary. और ये दोनों सरफेस पे हो रहा है, ये इस वाले सरफेस पे भी हो रहा है और ये इस वाले सरफेस पे भी हो रहा है. सो दोनों ही लॉन्गिट्यूडनल शेयर स्ट्रेस और सर्कमफेरेंशियल शेयर स्ट्रेस अराइज होते हैं in case of the pure torsion. Here is another question that it says that under torsion, brittle material generally fails. It fails along an angle of 45 degree to the longitudinal axis, whereas for the ductile material, that failure is 90 degrees. So brittle material in torsion, we have a failure of 45 degrees. Ductile material gets a 90 degree. Brittle material under tension gets a 90 degree. And brittle material under compression gets a 45 degree. Ductile material in tension gets a cup and cone or a 45 degree failure. Ductile material in compression gets a failure plane of 90 degrees. Then in terms of the ratio of ZP, that is polar section modulus of hollow shaft and polar section modulus of the shallow shaft, it is given as 1 plus k square, where k was what? Ratio of the inner dia over the outer dia of the hollow shaft over 1 minus k square. And since this ratio is greater than 1, we can say that the polar section modulus of hollow shaft is greater than that of the solid, which means that the hollow shaft is more strong with respect to the solid shaft. Therefore, the torque allowed, that is the torque carrying capacity, is more in case of the hollow shaft. As one can say, for a fixed permissible shear stress, tau is directly proportional to the polar section modulus, which in case of hollow is more, hence torsional capacity in hollow is more. Here is the strain energy comparison between the two. It is tau square by 4g. G is the rigidity modulus in times the volume of the shaft of a solid, and for the hollow it is tau square by 4g, 1 plus k square times volume. Again, for you comparing the formulas of the strain energy, you can see that the strain energy stored in a hollow section is more, than that of the solid shaft. So we have this key points, that is hollow shaft stores more energy than the solid at a constant tau max and volume. Also, solid stores more energy than the hollow shaft when it has same weight or volume and same torsion. You see, tau square u is written as t square dot l by 2 gj, and since it is inversely proportional to j, whichever has more polar moment of inertia stores less energy, but only when it has the same torque and same weight. But when in the case is having same shear stress and same volume, then hollow will be storing more energy. Again, the ratio of strain energy comparing solid to hollow under equal torque and weight is given by d square capital, that is outer dia, plus d square given by d square minus small d square. This is greater than 1. As you can see, it is solid by 2 hollow, hence this is greater than 1, which implies that at equal torque and weight, solid stores more strain energy. Again, Z hollow, we have discussed this before. Polar section modulus, we have discussed this below, above also. Here it says with the same area and weight and material, Zp of a hollow is more than Zp of solid. And in case the outer dia of the hollow becomes equal to that of the dia of solid shaft, then in that case only the polar section modulus of a solid shaft is greater than the polar section modulus of a hollow shaft. Again, torsion carrying capacity is the ratio of their polar section modulus. Torsional rigidity ka definition, that it is the torque required to generate 1 radian twist per 1 unit length of the shaft. You see, torque is gj theta by l. You keep theta as 1, l as 1, we get t equals gj. We discussed this before also. That torsional stiffness is torsional rigidity over length. Here is another question which asks the maximum normal stress given bending moment and twisting moment. The correct answer is 16 by pi d cube bracket m plus root under m square plus t square, that is C. As you can see, sigma 1 is 16 by pi d cube m plus root under m square plus t square. Similarly, the minimum is minus minor principal stress can be calculated using the minus sign. Tau max is 16 by pi d cube root under m square plus t square, which is also tau equivalent. We know these two formulas also. Here is another question which asks, when a shaft is subjected to combined twisting moment and bending moment, the equivalent bending moment is, well, in case of combined stresses, the m equivalent is root under, it was equivalent bending moment. M equivalent is 1 by 2 bracket m plus root under m square plus t square. As you can see, sigma b comes out to be in pure bending as 32 m by pi d cube. With pure twisting, we get shear stress, maximum shear stress as 16t by pi d cube. The combined effect is calculated and we find the principal stresses. Sigma 1 comes out to be this, sigma 2 comes out to be this, and tau max comes out to be this. Then we have the shaft in series and shaft in parallel. In this, the torque remains same. In this, the theta is equivalent to theta 1 plus theta 2. पार्ट्स में जो शाफ्ट्स होती हैं, एक दूसरे की जो ट्विस्टिंग है बाय एंगल, दैट वी कैन ऐड. So TL1 plus GJ1 is TL2 by plus GJ2. And here we have shaft in parallel, where we can write T equals to T1 plus T2. The theta remains same. And here we have to write in terms of GJ theta by L and GJ theta by L. In terms of stiffness, parallel में we write it as if it is parallel, and series में हम इसे we write as if the formula is of parallel in terms of stiffness, or parallel may we write as if it is in the case of series. In terms of radius, the polar moment of inertia is also asked. So it is simply pi by 2 r to the power 4 minus ri to the power 4. Then we have the torsional moment of resistance ratio of solid to hollow. We write it as 1 over 1 minus k4, that is d to the power 4 over d to the power 4 minus d to the power 4. This will be greater than 1. Then strain energy stored can also be written in the form of area under the t theta curve. उसका हम एरिया निकालते हैं. Then it comes out to be 1 by 2 t square L by gj. And then we have composite shaft similar to we have in the bars, that is shafts of 2 or more material. Just like in the bars we used to have delta 1 equals delta 2 equals delta 3 equals to delta. Here we have theta 1 equals theta 2 equals theta 3 equals theta, where delta is calculated as PL by summation AE. We write here as TL over summation GJ. Then we have bars and shaft. In the bars we used to have, it is in the composite shaft only, P1 plus P2 plus P3 equals P, and P1 used to be found out total load P into E1 A1 over summation EA. In the shaft we have T1 plus T2 plus T3 equals T. T1 can be found out as T dot G1 J1 over summation GJ. Then we have fixed shaft. This is a case which is similar to what we have in the first two chapters, where we get a load of P and we have A and B. We have to find out the P1 and the P2, and we often find it very easily. Something similar happens here. The concept is that the net deformation is 0 in fixed shaft or bar. I'm not going into the whole derivation or solution. The net twist is considered to be 0. So therefore the twisting in part A is equals to the twisting in part B in opposite sense but equal magnitude. We compare the thetas, that is TA over GJ, that is TL over GJ equals this. So finally we get TB equals to T dot A by L and TA equals to TB by L. Here is a comparison. Here we can see the torque at A involves this distance close to the B, and the torque at B involves A distance, similar to what we have in the first two chapters of strength of materials. That to find out the reaction, here we get PB by L, here we get PA by L. Similarly in this case we get PB by L here and we get PA by L here. This is a solved numerical where I can simply put TA equals to T times, at A I have to use 3, at B I have to use 2, that is T times 3 by 5, and I can easily solve. Similarly we have this where we have different torsional rigidity. We'll simply be using same thetas, that is TL by GJ1 TL by GJ2, and we will find out the relations. Similarly we have shaft of varying cross section. It can be written as theta equals theta 1 plus theta 2. This is more like a series. TL1 by GJ1, TL2 by GJ2. Solving this we get final theta. Then we have fixed shafts. Again this is similar to in series. Now we are comparing here the torsional strain energy with axial load and torsion load, where we have P square L by 2 AE, here we have T square L by 2 JG. Here we used to write sigma square by 2E strain energy per unit volume. Here we have for solid shaft as tau square max by 4G. For hollow shaft we have tau square max times 1 plus K square. So one can say that for hollow shaft the strain energy is more, and for a circular tube the polar moment of inertia is written as 2 pi r cube t. Here we have a variation in a composite cross section of shafts where we have material with G1 rigidity modulus and G2, and the variation will go something like this. In case G2 is more, the G2 stress will be at a higher place or having higher stress value, whereas for G1 it will be at lesser value, and in case G1 is more, so the G1 value will be more or higher than G2 value. So theta is given by TL by GJ. It is similar to Hooke's law. It is valid for a uniform cross section, and the force or torque should be constant. Again, theta is T by KT. It is KT is the torsional stiffness. So connection of shaft in series and in parallel, we just discussed. We write theta equals theta 1 plus theta 2. In parallel we have same angles. We just write T1 plus T2 equals T, and the ratio of strain energy per unit volume for a hollow section is like this, and for a solid it is like this. The ratio gives us greater than 1, that is strain energy per unit volume of hollow is more than that of the solid. Then we have a parallel connection. We just saw this question previously also. Here is an important result which says that the ratio of torsional capacity of hollow and solid shaft for same weight, that is for having same area and same material, it is T hollow by Ts equals 1 plus k square root under 1 minus k square. It is an important fact. This is the variation of shear stress we discussed earlier also. In this equation can also be used. Shear stress at the internal surface over outer surface is radius of the internal over outer. This is the question which I have uploaded in the community. I have solved this question, so we don't need to discuss here. And this is what we have in this revision. As you can see, comparing hollow versus shaft for same outer dia, the T hollow over T solid is 1 minus K4, and this ratio is less than 1, that is for same outer dia solid is stronger. For the same weight, T hollow by Ts is given by 1 plus k square over root under 1 minus k square, and this is greater than 1. Therefore, for same weight, torsion carrying capacity of hollow is more. And when there is same shear strength or permissible strength tau p, the ratio of the weights is given by 1 minus k square over 1 minus k to the power 4 to the power 2 by 3. यहाँ पे मैंने k की जगह n यूज़ किया है. And since this ratio is less than 1, we can say that hollow is lighter. So here the failure of torsion for brittle is 45, for ductile 90. In tension, brittle fails at 90 degree. In tension, ductile fails at cup and cone or 45 degrees. For compression, we get 90. Brittle in compression gets 45 degrees. So yeah, I believe that would be it. So we can end the session here. Thank you.